plowing ahead here and start digging into the physics a little bit more. We got to turn off the lights there. Okay. So one thing I want to point out is that these materials typically luminesce, meaning you hit them with a high energy photon, the exciton is created, and if that exciton does not find an interface to dissociate, the likely process is that it'll decay, giving off a photon, luminescence. So we can measure that luminescence as a measure of the efficiency of the quenching process, or how well the exciton has been dissociated. So one of the early experiments, and this was done at UC Santa Barbara in the laboratory of Onsager, was to measure luminescence as a function of the amount of acceptor that is in the material. So here's the luminescence intensity is this plot here, and on the log scale is the concentration of the acceptor. And this is molecular percent, mole percent. So what you see is very rapidly, even below 1% of the acceptor, the luminescence is quenching quite rapidly, right? That means the exciton is coming in, and it quickly finds a fullerene to break it up, and therefore it cannot give off a photon, so luminescence is quenched. If you then put electrodes on the device and measure the current coming out, what was found was that you need to go to a little higher percentage, close to about 15 or 20%, when that current really starts to turn on. So if you just have 1% fullerene, you can quench the exciton, you can dissociate the exciton, but you can't get the carriers out. So you need to get above the percolation limit to get the carriers out. And it actually agrees with percolation theory fairly well. So for percolation theory, if you're mixing two objects, two spherical objects, what doping level do you get a percolation path? It should be 16% from the theory, and that's about what we see in these materials. Okay, so then what are the kinetics for the working device? How do we get charge out? So we can sort of follow a pathway here. We start with a donor material, which is typically the polymer. Absorb a photon energy, H nu, to create the exciton. So D star is the exciton state with the star. Then there are some bad things that can happen. We can get luminescence, so that would be bad because we'd be losing our energy. We can also just go straight to the ground state without giving off a photon and just give off some heat, some delta H. That's also bad. Those are energy loss processes. What we prefer is diffusion of that exciton to the interface with the acceptor, with the A. So now you've got the exciton sitting right next to the acceptor, and then that ultrafast process occurs, that 45 femtosecond process. Now, there's tons of great physics in here, and as a community, we don't understand all of these steps. There's lots of different theories about what details actually go on here. I'll talk a little bit more about that tomorrow. But we generally agree that what happens is that first, that exciton becomes delocalized across the donor and acceptor. So the electronic configuration spreads over both molecules. And this would happen in a very short time scale, a few femtoseconds. Then there's a partial charge separation. A little bit of positive charge goes to the donor, a little bit of negative charge goes to the acceptor. We have a couple of names for this species. It's sometimes called a charge transfer exciton, so something like an exciton that has been partially broken up. Or it's called a bound radical pair, or bound radical polaron, a BRP state. And this turns out to be very important for the voltage that you get out of the device. So at that stage, then we rely on either some diffusion or electric fields to drive the charges away to get truly separated charges where you've got a positive polaron on one molecule and negative polaron on the other, on the acceptor. Right? So I'm calling these things polarons, meaning that you've got a charge sitting in a mean field of other charges, and that charge distorts the lattice a little bit. It distorts the field around it. Now that polaronic energy, which would be a self-binding energy, is not particularly strong in these materials. So it's not necessarily a polaron in the sense that you would find it in some inorganic materials. But we still oftentimes refer to them as polaronic conductors. So anyhow, hopefully the positive polaron would go towards the positive electrode and the negative towards the negative electrode. Okay, so a little bit of spectroscopy for the spectroscopists in the audience. How do we measure that 45 femtoseconds? So this was done by my old postdoc mentor, Christoph Brabetz, who at the time was in Linz, Austria. He is now in Erlangen, Germany. But this was done with the pump probe experiment. So you come in and you pump the donor, and so its absorption In this case, peak absorption about 500 nanometers, so you come to the strong 500 nanometer. And then you do absorption across the whole spectrum and see what you see. So at a very short time scale, you see, so this plot is delta T over T, the change in transmission over the original transmission. So above the axis is a positive delta T over T. Okay, here's a trivia question. So what does that correspond to? This is a term I believe was mentioned yesterday. If you have a positive delta T over T, what does that correspond to? This is a tough question. If you have a white t-shirt and you get a stain on it, what do you use to get the white stain out? Bleach, right? So this is a bleach of the states. So what happens is with the pump, you've created so many excitons that now there's extra transmission because the probe comes in and goes through the material. So a positive delta T over T is a bleach. So originally you see that. And as we look in time on a femtosecond time scale, what we see is now a negative feature that comes in at larger wavelength. So the negative feature is an absorption. There's a new species that is absorbing the probe. And in this case, the new species is the charge separated state. It's that polaron species that's absorbing. And the polarons tend to absorb at a little higher wavelengths. So past 600 nanometers, actually far into the infrared, they can absorb. So we can monitor that absorption in the infrared on an ultrafast timescale and see the growth of the charge separated state. You can also just sit your spectrometer on a given wavelength. In this case, it's at 700 nanometers. Well, this is at 500, this is at 700. Sorry, the print is really tiny. But you see this decay of the signal as a function of time. And this time constant is something like 45 femtoseconds. So we really have this ultra-fast process. More recently, what has been measured is to do the pump probe, but in the opposite direction. So one can pump into the fullerene. The fullerene absorbs a little bit, particularly at high energy. And you can see hole transfer, positive transfer in the other direction. And you do the same type of spectroscopy and you find that that's an even faster process. That's something like a 30 femtosecond process for the hole to go over to the polymer. So both processes much, much faster than much of the other things happening in the system. Okay, so once we have those separated charges, we would like them to live a very long time in order to be transported out of the device, something like a microsecond or several microseconds. So how do we measure that? Well, there's a number of techniques. The technique that we like in our collaboration is called TRMC, time resolved microwave conductivity. So this technique measures on a time scale of a few nanoseconds all the way out to milliseconds, if you like, or even seconds. And what it is based on is basically the change in dielectric constant associated in a material when you have free carriers. So what we do is take our sample and we put it into a microwave resonant cavity. So that cavity is maybe 15 centimeters long, a few centimeters wide. It's just a rectangle. And that's resonant with an 8 gigahertz or X-band microwave. And so we put the sample into that resonant chamber, we turn on the microwave beams, the 8 gigahertz, and what happens is that the free carriers attenuate the microwave signal, or absorb the microwave signal, through a change in dielectric constant. So if we look at that change, so the power minus the loss of power, P minus delta P, or we take the quantity delta P over P, that is directly relative to the change in conductance of the film, delta G. So K here is some geometry factor dealing with the nature of the microwave resonant cavity. So what we're measuring is a change in conductivity. Now the conductivity has two factors. It has the carrier density, N, or P, so N for electrons, P for holes. Also has a mobility term. That's mu for electrons, mu E, or mu H for holes. So what we measure with this technique is actually a sum of the two carriers, or rather the two carrier densities, times their respective mobilities. We don't measure directly either N or mu, but we measure the summation. That's one of the limitations of this technique. So anyhow, here's just a diagram of the setup. So we start with the Yag laser. Again, here's that OPO, the optical parametric oscillator or amplifier. So from that we can get a range of wavelengths really throughout the UV up into the visible, up into the IR. And there is this thing called a circulator, which is just a round microwave cavity. And off of that circulator is, there's the source. This is our 8 gigahertz source, the X-band. And then, well, so here's the sample. The sample is sitting here. And then you have a detector. So microwaves come in, they get attenuated, they come in here, they circulate, they get attenuated, they come back, they get detected, and then we have that attached to a oscilloscope to get a time trace of the signal. So when we come in with a pulse of light, this light pulse is 5 nanoseconds, we create a population of carriers, we reduce the microwave beam, and then as those carriers disappear through recombination, this signal will come back up. And so we're measuring the time decay of that signal. So as an example, so here is the y-axis is our measurement. So what we plot is called phi times sigma mu. That is the quantum yield, so how many electrons are produced for every photon that comes in, times the sum of mobilities, the sum of the electron and hole mobilities. So this is the output from the TRMC. So this is the time scale. So what you see is an initial growth, which is the creation of the charges. There's also a convolution of the time response of the cavity. So one limitation is the cavity itself has a time response of a few nanoseconds, so that limits the time response of the measurement. So it's not an ultra-fast measurement, it's quite a slow measurement. So here's the time response of the cavity, and then you see the free carriers, and they're living here. And on the time scale of 150 nanoseconds, there's essentially no decay, right? So that's almost flat there. Now, you see a bunch of curves. What are the bunch of curves? Each curve is at a different intensity. So the top curve here is at an intensity of about 10 times the sun, or 10 suns. So a sun is about a kilowatt per meter squared, 1,000 watts per meter squared, or 100 milliwatts per centimeter squared, right? If you go outside, maybe not today, but on a bright day, that's essentially what you would measure. So in this technique, we're generally operating many-fold higher than that intensity. So we're operating somewhere between 10 suns, 1,000 suns, we can go up to 1,000,000 suns with the measurement. So what happens is, at very high intensities, now you have lots of excitons in the system. You also have lots of carriers in the system, electrons and holes. So when an exciton meets a carrier, that's bad news for the exciton. The exciton dissociates. So then you wind up with, originally you have an exciton and say you have an electron. They interact, then you just have 2 electrons and a hole. The exciton is gone, and then we lost the energy of the exciton. So you see that at very high light intensities, where now the phi sigma mu, the quantum yield times sigma mobilities, is very low, because the phi becomes very low. So anyhow, that's one of the details of the experiment. So, but we can get a lifetime out of this curve, particularly at low suns. It's easy to do, and we do measure lifetimes of about 1 microsecond at room temperature, depending on the materials. Okay, so that's how we can see how the carriers live. Now, how do they get out of the device? I mentioned that there's both drift and diffusion forces, right? So drift depends on the existence of an electric field. And we can draw a very simple diagram of the electric field. If we take our materials and we draw our levels, so here's the HOMO, the highest occupied molecular orbital of the polymer, and LUMO of the 60, the lowest unoccupied molecular orbital. If we make a really good device, then we connect the cathode, or the negative electrode here, we connect the anode, or the positive electrode here, where we tailor those electrodes. When you put it into short circuit, that means you are connecting the anode to the cathode, just connecting a wire here. They must be in chemical equilibrium. They must have the same chemical potential. That means they have to line up. And the only way then to meet the requirement of them lining up is for there to be a tilt in the bands. And so in this axis is energy, this is distance, this is energy, this is distance. So now you've got a changing energy with distance. You have a dE dx. And from second semester physics, you know that's an electric field, right? So now I've drawn a constant electric field in that device. And that's called a built-in field, and that is going to depend on the distance or the energy difference between these two levels and how well one lines up the electrodes to those levels. So assuming you've done that perfectly, you then hit the system with photons, and if we disconnect the wires from the device, then these electrodes are free to move to whatever chemical potential or whatever voltage they like. And if I'm coming in with photons, then that difference is driven by what's called the quasi-Fermi levels. So we can define the Fermi level, right? That's the chemical potential for a type of charge. You can also define it for the electrons and the holes separately. So two separate Fermi levels. So the green would be the electron Fermi level, quasi-Fermi level. The orange would be the hole quasi-Fermi level. And as you pump more photons in the system, create more charges, the splitting of those Fermi levels becomes larger. And this splitting is what then makes the voltage in the device, right? So you might suspect that the more photons you have means the more voltage you get out, and that's in fact the case, right? That makes sense. So that means fundamentally, if I have a brighter sun, I can get more voltage and therefore more efficiency out of the device. So any photovoltaic device, be it inorganic or organic, will be more efficient at a higher intensity, right? So that's one reason why we can make very tiny devices, put a big lens in, focus down the lens, and get very efficient devices is through this process. Okay. Any questions on quasi-Fermi levels? Have you guys had solid-state physics? Yeah, okay. So one point becomes that you can see right away that the splitting of these bands from the very beginning places a limit on the voltage of the device. So these quasi-Fermi levels cannot exceed the energies of the bands, right? We can't drive the electron Fermi level past the LUMO of the C60. So that presents a fundamental limit. So if we sort of draw the diagram as we separate the two materials, here's the donor, here's the acceptor, and then we can define this difference between the two as the effective band gap of the system. Right? Normally if I give you one material, you can say what is the band gap. For silicon, it's 1.1 electron volts. Now we have two materials, we're going to say we'll make a funny definition for band gap being sort of this cross material band gap, which I call the effective band gap, between the HOMO of the donor and the LUMO of the acceptor. So that places an absolute upper limit on the voltage, is this effective band gap. Now in reality, you can never reach that ideal limit because there's recombination processes, there are other limitations, so our voltage is always substantially less than that. Okay, so let's put some numbers on that band diagram. So here's our P3HT, here's the fullerene PCVM. And so roughly the HOMO of the P3HT is at -5 electron volts. The LUMO is at about -2.9, so it's pretty close to vacuum. Right? Vacuum's up here somewhere. And the LUMO of the PCVM is much lower down. In fact, the difference between the LUMO and the LUMO, which we'll call the band offset between the materials, is over a volt. It's a huge, huge band offset. And then its HOMO sits down here somewhere. So this gives you an effective band gap of about 0.9 electron volts. So you can see that perhaps this is not an ideal system from an energetic standpoint. So the most voltage we can get out of this system is 0.9. And in fact, the data I showed you, we actually get about 0.6. We lose a third of that voltage. So you can also see that with this really large band offset, that when we have the exciton here, we transfer the electron, there's a large loss in energy. We started with an exciton that had roughly 2 electron volts, or about 1.9 electron volts in energy. And we already lose over 1 electron volt. So that's all energy loss, which is a bad thing. So something I'll talk about a little bit more tomorrow is how we can tune this band offset, try to minimize that, and get higher voltage out of the device and not lose so much energy. Now there's a reason to have why this works so well, is if you have a very large band offset, this gives you a very large delta G, very large driving energy, a free energy for splitting the charges. And there's a couple different theories that are being debated as to why that could be useful. One of them is that when you have the charge transfer, where does that 1 electron volt go? Well, it has to go into the lattice, it has to go into phonons. And those phonons can then assist in the separation of charges. So electrons and holes can be essentially vaulted away from each other just from phonon-assisted processes. And that was discussed already many decades ago in a famous text by Pope and Swinburne. But there's another description of this based on Marcus theory. So Marcus or Marcus-Hush theory, describes electron transfer between molecular systems, and we can use that to discuss this band offset energy as well. And again, we'll do that in more detail tomorrow. Okay. So a little bit more detail about the charge separation process. So there's a theory extending way back to the 30s that describes the actual separation of the charges from the exciton, or the dissociation of the exciton. That's called the Onsager theory of charge separation. And the idea is that you essentially have electron and hole that are placed in some proximity to each other, and they are subject to each other's Coulombic attraction, right? So the electron feels the hole feels the electron. But they're free to roam around randomly. They're doing random hopping, kind of Brownian motion, subject to this Coulombic interaction. And additionally, you apply an electric field. So there's an electric field on the system, right? These guys are hopping, they're being attracted, and then there's a field that wants to push them in opposite direction. So Onsager worked out the physics for that, and you get a probability for dissociation. I know you can't see this because I can't see it, but it's a function of their distance r, and the angle here is between their dipole and the field f, that angle theta. And essentially it's an exponent of 1 over kt, and then an exponent of the field, and then a summation. This is an expansion over some kind of spherical harmonic that involves the cosine of that theta and the field strength f. So I'll let you go read the 1938 paper if you want to see the equation in detail. But the bottom line is that if you start the charges at a given distance, you can start them at 100 angstroms apart, and measure the probability for dissociation. So this is efficiency of dissociation. So 10 to the 0 would be 1, 100% probability for dissociation. As you turn up the field, that probability, of course, goes up. And it has kind of a sigmoidal structure, so you hit sort of a critical field and it really takes off. Okay, so this is our fundamental description for charge separation. And we can think about the reverse process. So you have two charges very far away, again randomly hopping, and when they come close, they start to feel their Coulombic attraction, and the worst case scenario is they recombine. So that process can happen, and that's called Langevin recombination, which is the exact opposite of the Onsager charge separation. So Onsager, Langevin. And we'll discuss the Langevin equations in more detail tomorrow as well. Okay. So this now brings up one of the big mysteries in organic photovoltaics. So according to Onsager, if we start with an electron and a hole that are only about a nanometer apart, to break them up, we need a field strength of at least 10 to the 5th volts per centimeter. This is a very high field in order to break those apart. And in the device itself, we're really operating about 1 or 2 orders of magnitude less than this. So the field strength along the curve of the JV curve is something like 10 to the 3rd to at most 10 to the 4th volts per centimeter. So strictly according to Onsager, the electron and hole should never break apart, and these devices should not work. But they do. We get about 90% of the charges out at peak wavelength. So this is not the whole story, and there's lots of explanations for what other physics might go into this, but that we'll discuss a bit more tomorrow as well. Okay, so I'll do a little bit of device modeling here. This is an older model that we did already 11 years ago, 10 years ago, and we have a little more sophisticated models now, but this is a very good, I think, basic description. So we have our device equation, which involves diffusion terms, so D is our diffusion coefficient. This is now the second derivative in time of the carrier density, n, as a function of x, the position in the device. This is a one-dimensional model, so we just worry about the position x. Then we have a drift term. So here's the mobility, that's the velocity divided by the electric field. Here's the electric field, it's the voltage divided by the thickness. And then here's the first derivative of the carrier density. Then there's a recombination term. So the carriers will disappear, they'll recombine with the characteristic lifetime of tau. So that's the characteristic recombination lifetime. That's negative term, that means the carriers are disappearing. And then there's a creation term. So we have photons coming in. Photons are absorbed with a cross-section of alpha. There's a rate of them coming in, which is some n. And then there's an exponential decay, just following Beer's law of the absorption profile. So you put all those in, you put in some characteristic numbers. So a characteristic absorption would be about 10 to the 4th per inverse centimeter. So fusion coefficient is about 0.4. 4 times 10 to the minus 3, and a typical voltage might be 0.8. So you can then plot this out for different mobilities, right? So different velocities of the carriers. So a very simple picture. As you increase the mobility, and here the mobility is increasing for each curve, you see that the maximum position of the curve increases. So first of all, why is there a maximum position? Well, when you have a very thin device, it's not absorbing very much. When you make it thicker, it starts to absorb more, so you get more carriers. That's the positive slope here. If you get a very thick device, then you have lots of carriers, but they have a long distance to travel before they recombine. So this current starts to decrease. So somewhere in here is an optimal thickness for the device, where the competition between creation and recombination balance out. So when you increase the mobility, you see that allows you to make a thicker device, and also, of course, the total current you get out of the device is more. So at least from a very simple picture, higher mobility, higher velocity is better. Now what this model fails to include is that this recombination term, tau, that also depends on mobility. And the Langevin process, which I just mentioned, has mobility in the recombination rate. So this tau goes down as mobility goes up, meaning that can also, as mobility goes up, that can decrease the current, right? And in the more advanced models we have include those terms. So anyhow, this is a basic picture. Fast carriers is generally good. Okay, so I just want to cover one last topic for today, which is this issue about morphology. So I showed you pictures saying that when you mix the polymer and the fullerene, it's not completely uniform. And the uniformity of that mixing is very important for the charge transport and the recombination. So first, to go back to some very basic charge transport theory. These are very disordered materials. You can see from the pictures, and you can imagine that if we're just coating this solution, that the polymers are folded and entangled. We're basically making a spaghetti. So it's nothing like the crystalline lattice. So we don't have a periodic lattice. We can't write down block wave functions. So we can't make a wave function that looks something like a periodic function with a wave vector k. Just can't do it for the most part. So instead, we're going to rely on a hopping theory of transport in disordered materials. So this course goes back to the days of Sir Neville Mott, and even back into the 30s for studying transport in disordered materials. But the basic premise is that the material consists of certain sites. So the site can be occupied by a charge. In this case, there's maybe a positive charge on site I, and that charge can hop to site J through a thermally stimulated process. So one can define a hopping rate, which, for instance, under the Miller-Abrahams theory, the hopping rate would be nu ij. That's the rate to hop from I to j. Let's focus over here. Here's the temperature term. So there's an exponent of the change in energy between site I and site j, and there's a kT term, right? So there's the thermally stimulated process. So if the energy of I is smaller than the energy of j, then this is a negative number, and it's an uphill process. And therefore, higher temperature is better, right? The higher temperature will kick you uphill faster. If, in this model, if you're going downhill in energy, so energy of I is greater than energy of j, we'll just assume this number is 1, right? There's no super charge transport, but we'll just call that term 1. There's another term in this formulation which has to do with the molecular orientation. So we can define an energy for each one of these sites, but we can also define a molecular orientation. These things are amorphous, and we can imagine many different orientations that are possible. And the relative orientation between the two molecules also can dictate the rate to an exponential term. So we put all these terms together. There's a nu naught, which is a fundamental attempt frequency. That is, how many times can that charge potentially attempt to do a hop within 1 second? This is a bit of an arbitrary factor, but we usually make it about 10 to the 12 or 10 to the 13 per second on the time scale of the phonon vibrations of the molecules. Okay, so what one can do then is use that microscopic description, that molecular level description, put that into a Monte Carlo simulation, and then describe charge transport on a lattice, and come up with a global description for the mobility, that is the velocity divided by the electric field, as a function of the statistics of the energy in the lattice. So what are the statistics? Well, if we populate the sites with a Gaussian distribution, an energy, which is what we typically do, then we can define sigma, or the variance in the energetic landscape. And that defines the amount of disorder in the material, right? So if that sigma is very broad, we have a very disordered material, and those hops can take place between much different energies on lattice. So this was all worked out back in the 90s by Heinz Bessler at Bayreuth University. I could have that wrong. But he determined that you could get a global mobility as an exponential function of the sigma, and another constant thrown in there, and a square root of the electric field. Now the square root dependence in the exponent, that's a very common feature for charge transport in the materials. That was studied already decades ago. It's called a Poole-Frankel mechanism for charge transport. So you get mobility times the exponent root of electric field. And you see that in all these materials. So at the time, this model fit to charge transport pretty well in a lot of experimental systems, but it did not fit it for a very large range in field. So you could maybe change the field by 1 order of magnitude and the model would fit. Change it by 2 orders of magnitude and the data started to diverge from the model. So what was subsequently tried in the late 90s and the early part of the 2000s was to, instead of using completely random energies in the lattice, to correlate those energies, right? So if I put an energy here at 0.2 electron volts, then the energy here is likely to be closer to 0.2 electron volts than the 0.3 electron volts. So it's called a correlated disorder model. I should mention that this is called the Gaussian disorder model because we use Gaussian energies. This is the correlated disorder model. So here you get something that functionally looks very similar, but some of the terms look a little bit different. Instead of a 2/3 here, you get a 3/5. Instead of some arbitrary constant here, you get exactly 0.78. And here you get sigma goes into this term in the square root of the electric field. A number of people looked at this, and indeed this gives you a better description to experiment, and you can use this to fit over a wider range of fields. So the bottom line is that the molecular ordering, both the orientation, the distance, and the relative energies between molecules is critical in determining the velocity of the carriers through the film. So I should mention that these are all thermally stimulated processes. As you turn up the temperature, the hopping rate increases, and so the velocity also increases. This is the opposite of a conventional semiconductor like crystalline silicon, where you increase photon scattering at higher temperature and mobility goes down. So there was a question between the break about what happens when you take these solar cells and put them outside. Are they going to heat up? The answer is yes. And typically, if you put a solar cell on the roof, it will reach something between 55 up to 60 degrees centigrade. If you go into the desert, you might see 80 degrees centigrade. So that's actually can be a good thing for organic solar cells because now the velocity of the carriers actually gets better at higher temperature. In fact, their performance tends to be better on 50 degrees centigrade than at room temperature. Okay, so what is the impact of all that morphology stuff? That means the way we process the materials and the way we make the films will be critical in determining the efficiency. So this is kind of an old story that I've told already too many times, but back when I was doing my postdoc, we had some of these basic materials. Here's a polyphenylene vinylene derivative, PPV derivative. Here's the PCBM guy. And we just started changing the solvents that we're using to dissolve the material and to cast. And one of the common ones at the time was a toluene film, and we decided to go with chlorobenzene for a couple reasons. But what we can see is that at least from an atomic force image, and I apologize, there's a scale bar here, this is about 5 microns across. You see really much different topology in the image. And back then we didn't have very good microscopy tools, that's about all we could really discern. But these days the microscopists can do a much better job and can get 3-dimensional images and lots of different techniques are used. But the upshot was that when you change the solvent, the current density, so here's the toluene, the short circuit current originally was about 2.5 and went to over 5. So we doubled the current in that device. The voltage was about the same. The fill factor went up a little bit. It started at 0.5, went up to 0.6. In the end, efficiency was 2.5%. So that was close to a tripling of the device efficiency. It was a world record for at least 6 months before it was exceeded. Okay, so we did have at least a cross-sectional SEM. Actually, this occurred a couple years later after I left Austria. And they did the same thing where you take the device, put it into an epoxy, let it harden, dip it in liquid nitrogen, make it very cold, and then just break it. And you can then do a cross-sectional SEM in this case. And you see from toluene, you get these really big bubbles of polymeric material surrounded by smaller bubbles of fullerene material. At least that's what we think the two material components are. So this looks a lot different than that ideal cartoon I showed you where the polymer and the fullerene are kind of uniformly mixed. Chlorine, the chlorobenzene case, you get a much more uniform mixture between donor and acceptor, meaning that the exciton that's generated has a shorter distance to go before it can meet an interface, can be dissociated. So this is closer to an ideal morphology. Now that exciton has a very short lifetime, about 300 picoseconds, and it's not very mobile. Its diffusion coefficient is pretty small. So it can only go about 5 or 10 nanometers before it either radiates a photon away or collapses to the ground state. So we need this mixing to be much more intimate, as in this case, as opposed to this case. Okay. Not only when you change the solvent, you don't only change the mixing of the donor and acceptor, but you also change the morphology of an individual material. So if we look at the neat material, so by neat we mean unblended, just the material by itself, and we change the solvent, and we're changing the way the molecules are packing, and we're changing the velocity or the mobility. So again, it's a little bit hard to see, but what we did was make transistors. So we make a field effect transistor, which is a common way to measure mobility. And in the toluene case, we measure in this case about 5 times 10 to the minus 6 centimeters squared per volt second for mobility. And the chlorobenzene, we get about a factor of 50 higher, 3 times 10 to the minus 5. So in fact, what's happening here is chlorobenzene is not a very good solvent for the polymer. Right? Toluene is a much better solvent. So when you dissolve the polymer in the toluene, you get very good dissolution, and then the polymers tend to pack in a more arbitrary way. It's more random, more spaghetti-like. Chlorobenzene is not a very good solvent, and in fact, at certain concentrations, this is not a solution, but is a suspension of material, colloidal suspension. In this case, the polymer chains would prefer to stack on top of each other in a more rigid fashion, and to reduce their surface area to the surrounding solvent, which is a poor energy of interaction. So a bad solvent actually gives you a better mobility because you get better stacking up of material. Okay. So another effect you have is that as you change this donor and acceptor mixture, they influence each other's morphology. And so we saw something very interesting already 9 years ago. So if you look at both the whole mobility, there's a positive carrier mobility and the negative carrier mobility as a function of how much of the fullerene you're putting into the film. So you can start with 0 fullerene, and this is now just the pure polymer. As you add fullerene, the mobility of the holes goes up. So this is a bit counterintuitive, right? So I'm adding some component that is diluting the whole transport material, but the mobility is still going up. So what's going on? Well, it turns out that as you put in the fullerene, it helps the polymer to pack a little bit better. And you get better pi stacking, pi electron stacking, and you get better transport. Now that has a limit. If you go above 80%, now you really start to dilute the polymer and it starts to come down. But at those levels now, the electron mobility starts to turn on. And so actually at about 80% fullerene and about 20% polymer, these two mobilities are roughly the same. And that's in fact where we make the device, is at an 80% fullerene mixture. Now this story has gone on, and there's a lot more recent work. And some of the work out of Stanford from Mike McGee's group has examined how exactly the fullerene fits into the polymer. And it turns out that in this case, that the fullerene fits, see, I have a diagram here. Yeah, so the fullerene will fit basically between, if you imagine there's a phenylene here, and this is an alkyl chain, alkoxy chain. If you go a little bit longer, there's another phenyl, another alkoxy. Fullerene fits exactly in between those two. It really nestles nicely in there. That's probably a bad thing. If the fullerene and polymer are very close together, that helps in the recombination process. So the negative charge and the positive charge will come together very quickly. So in order to avoid that, you have to put in lots and lots of fullerene so that you get a phase or a domain that's pure fullerene. And then you can avoid this recombination process. So that's why we operate this at such a high amount of PCBM. Other materials don't have that intimate mixture and operate closer to 50%, where you would expect would be a balanced charge transport. Okay, the story continues. Another thing you can do is once you've made the film, you can heat it up a little bit, do some annealing. And this gives a little bit of motility to the polymer chains, and then you cool it down, and they will then self-align a little bit. So you can get better charge transport and get the structures that look a little bit more organized, a little bit more crystalline through thermal annealing. So this was looked at again already 8 years ago, and if you look at, this is the incident photon per converted electron, essentially the quantum efficiency for every photon coming in, how many charges do you get out. So before the film was annealed, you get something like a peak of 30%, and then you anneal it and it goes up to something like 50–60%, right? So making these organized structures is a good thing for charge transport and generally a good thing to prevent this charge recombination. Okay, and I mentioned before about the slow drying process where we use a high boiling point solvent and put a petri dish over it. That was developed at UCLA at the Yang group. And this makes a quite fine spaghetti of donors and acceptors. On the surface here you can see in the AFM. And sorry, here's the donor and acceptors. So this is another technique for controlling morphology. But since I described it, I'll go on. So the morphology issue has a couple different components. So, or let's say constraints. So first of all, we want the average domain separation between the donor and acceptor to be about twice the exciton diffusion length, right? If we form an exciton in the middle of the domain, we want it to be able to make it to the interface. So you want the domain to be about twice the exciton diffusion length. At the same time though, if you make it too small, to make the domain very small, then you easily dissociate the exciton, but then the carriers will not have the opportunity to get very far away. So the recombination will be very high. So these are competing constraints. One likes a big domain, one wants a small domain, one wants a big domain. And we can just see a cartoon picture of that. So if we have domain is too big, the exciton will not make it to the interface, so it will not dissociate. If it's too small, we get lots of charges, but then the charges can't get away from each other. So we want something that's just about optimal for the domain size. Okay. So we can study this. We've sort of done a case study of this, sort of accidentally we've done this. By looking at a class of materials that makes a very fine mixture between the donor and acceptor. So before I showed you the polymer P3HT, what we can make is a molecular version of that. This is a dendrimer, or sort of a dendrimer, where we have a central core, and off of the central core are a number of arms. So the chemist can design this to have a variety of numbers of arms, can change the length of the arm, can change the substituent groups on the arms, can do all sorts of things. So we took this system and blended it with PCBM, right? So this is a light absorber system. It's similar to the polymer P3HT. Blended it with this PCBM stuff and expected we should get this great result because this is a nice pure material, very high purity. And we tried for actually a couple years and in the end could not get above about 1.5% efficiency. Even though with the polymer version we can get over 4% efficiency on a good day. So in fact, this is some of the best device data we have. We have an efficiency of 1.3%. Current is very small at 3 milliamps. I showed before we can usually get about 10. Voltage turned out to be a little bit higher because that homo-lumo offset was a little bit higher. But the fill factor, the sharpness of the curve is not very good. And you see that reflected in the quantum efficiency, which is also quite low. So what's going on here? Well, we go back to the morphology issue. So we can use just the AFM, use tapping mode AFM, and look on the top surface, and this gives us some little hint. So here is P3HT PCBM, sort of an optimal morphology, and you can't really make it out, but we presume that the bright spots are one phase and the dark spots are another phase, and that length scale is really about 10 nanometers. If you go over here, here's the dendrimer, and there's sort of a code name for it, but this one is called 4G13S. Mix the dendrimer with the polymer, and at least from here we get the idea that the mixing is much more intimate, much more fine mixing. We didn't have access to the transmission electron microscope at the time, but we actually need to do that to sort of confirm this. But it looks like this is a more finer mixing. If we go to the TRMC measurement, what do we see? Well, the blue curve is for the P3HT, and here you see a decay with a length scale of something like 1 over tau of about 100 nanoseconds, and the red is now the dendrimer, and of course it's much shorter. Here 1 over T is something like, 1 over E is something like 30 nanoseconds. The carriers just are not living as long, they're recombining much faster. So we think that this is evidence that the blending of the materials is too intimate, and this kills our efficiency. So actually, just to wrap it up here, we also followed this up with some molecular dynamic simulations. So we can do this in silico in the computer, and take a chunk of polymer, for instance. So here's 1, 2, 3, 4, 10 thiophenes, and put that next to fullerene. And we're using density functional theory. We minimize that structure, and then we measure the energy of the interaction between the polymer and the fullerene. So this is the minimized structure. You see that the ball tends to sit right in the middle of the chain, and that energy is about minus 12 kcal per mole. If we then do that with the dendrimer, we then minimize the structure, and you see that the dendrimer likes to wrap around the fullerene. And you get a much more intimate structure. The two are much more miscible or blendable in each other. And if you calculate the energy, you get something a little bit deeper, minus 14 kcal. So this is a more stable structure than that one. So I think there's some evidence that these two really like to mix at a very intimate length scale, and that now carrier recombination between these two is very rapid. Right? So this was a couple years ago, and we now have some molecules that we've designed that we think prevent this a little bit better and can lead to a little better devices. So it's now 3:30, and I think we have a football match scheduled. So I think I'll wrap it up there, and I'm happy to take questions. We'll continue more tomorrow.
When you measure transmittance on the femtosecond scale, how did you have like a laser, you have the detector?
Yeah, so it's a pump probe experiment, right? So you have an ultrafast pump. This is 10 femtosecond pump. You create the exciton population. The exciton is dissociated into carriers, and then your probe comes in, and then you probe the absorption as a function of time.
So you have a fast detector?
You have a fast detector. You can do this as a street camera, or what you can do is a path length change, right? So you've got the 2 mirrors, and you separate the distance and probe the signal at a various path length, which corresponds to a various time on your clock. It can be done either way. To be honest, I don't know how Christoph did in that particular experiment. Yeah. I'm not an ultra-fast spectroscopist, so I think others in the audience may be more versed in that.
I have a question. So in the cryo-TM image that you showed, so there are those like chain-like looking features there. So do we have just yeah, so do we have like pi stacking of
Yeah. Okay, you can't see it anyway, but yeah, the idea, as I tried to explain, is you have pi stacking, so there's sort of a multi-order hierarchy of organization. So imagine polymer chain, roughly 10 or 15 monomers long, is pi stacked, right, like my arms, and then that whole structure gets forward into the fibril. So take that structure and then grow it lengthwise into the fibril. So it has different order at different length scales. And that's been determined by some more recent TEM data by Julia Shu, my collaborator, where they have even better resolution and can look at individual fibers. Yeah. So, I mean, it's very analogous to liquid crystal structure at that point. It just does not exhibit the same sort of differential calorimetry that you would see in liquid crystal in terms of different phases and different transitions. But all the driving forces are the same. If you make these chains longer, if you make this into a 10 or 12 carbon, then you can get really liquid crystalline behavior. and there's been a fair amount of work on that. One of the best polymers in transistor work is a liquid crystal, right? BB-triple-T. But so far, none of the liquid crystals have yielded really high efficiency for a solar cell. They're good for charge transport by themselves. When you try to mix the donor and acceptor, those very long side chains tend to impede charge transfer.
Okay, I see. But with respect to those columns,
Yeah.
stacks,
Yeah.
they would PCBM.
So the thinking is that there are probably actually 3 phases of material. So the white lines are pure P3HT with no fullerene. And then the black is either a pure fullerene or is a mixture of polymer and fullerene that is very disordered. It's an amorphous phase. So we think there's actually 3 phases. Yeah. And there's some debate. Some people say you need the 3 phases, that the amorphous phase between polymer and fullerene is mainly responsible for generating the free carriers. And that is then the pure phases that act like highways to take it out. But then others think that the amorphous phase would be very good for recombination, and therefore you want to get rid of it. So that's one of the big discussions in the field. How many phases and what the actual nanostructure should be.
Do people draw some analogies with J stacking and H stacking?
Yeah. So when these are truly liquid crystal, you can get a certain offset in the stacking, and you can get different types. Typically, it's not exactly a J or H stacking in these materials, but in some small molecules, you can in fact get true J and H stacking. Yeah. So far, none of those have yielded very efficient devices. One of the problems is that when you get very good stacking, that the exciton can exist, can be spread out across 2 polymer chains, and that's probably a bad thing. You want the initial exciton just on a single chain.
More questions?
Great.
Thank you.
Thanks, guys.
For providing